Swayam Prabha. Digital India. Educated India.
I work in the security intelligence division of IBM Security. So Mahesh is my peer, and this was 2 years ago when people were talking about cognitive and all that. IBM had a huge mission to make everything cognitive, and it was also shoved down our throat to pursue something that's cognitive in security. At that time, when we began this project, it never occurred to me that we could use something like Watson for doing security analytics. Okay. Nevertheless, it got interesting, and then we began going down the path of applying cognitive sciences and use it for security analytics. For those of you who haven't heard about Watson, right? Watson is this umbrella of products where we use cognitive things to do multiple product lines. You probably heard about Watson for Health, right? Watson for Health is basically, Manipal Hospital uses it. It basically is digesting a lot of information that is out there, from clinical studies to blogs, to seminars, to journals. So we all ingest that data into this huge machine called Watson. And what it does is it comprehends all that information, tries to understand the language of medicine, and tries to help a doctor diagnose a problem. So it's humanly impossible to stay on top of everything, right? And more so with the medicine, because there's this latest research, there's latest clinical studies and all that. So especially in this part of the world, I can't imagine doctors traveling to a lot of conferences. There's hindrances because of economics themselves. You probably don't have access to the latest clinical studies that's probably being done, sponsored in the United States or someplace. So for them, it's really a great tool. You give Watson certain diagnostic information, and it'll go dig through all this millions and millions of documents. In a few minutes, it'll come up with what it thought about that particular medical report that you got for a patient. And then it would basically come up with a line of treatment that would work for that patient, right? And it doesn't mean that it's making the decision on behalf of a doctor, but what it's telling you is, okay, I looked at this information and I believe this is the right line of treatment, and the doctor could make the right decision. It's ultimately up to the doctor to make the decision. Okay, that's nothing to do with security, right? This is medicine. So same thing. The problem of cybersecurity is interesting too. We have a huge skill gap. Okay, we're looking for security analysts who are well versed with the latest attack patterns, who are on top of the technology, or on top of the game, understanding, what's going on, what's the latest, is it relevant to me, that kind of thing. So it's a similar problem in that, it's impossible to basically for someone to read all security journals. Lockheed ransomware or WannaCry, because you only get to know about it only after the fact, right? And it's very hard for security analysts, and let alone for an incompetent one, you're losing the game there. So the use case certainly applied to cybersecurity there as well, right? So what we tried to ingest this huge amount of security journals. And if some malware was detected, obviously the first thing that will happen is somebody writes a blog about it. WannaCry, if you could imagine, and go search for it. Somebody would have explained how WannaCry unfolds, right? It's a ransomware, it encrypts your system, and then somebody has to pay the ransom through bitcoins, and then get their disk unencrypted. So somebody went and explained what are the typical indicators, right? What are the hashes that you typically see with a WannaCry ransomware? How it unfolds, how it spreads, what is the lateral movement, what is the exfiltration patterns and things like that. So all of that is documented in a blog. So for a security analyst to basically say that, yes, you're infected with WannaCrypt ransomware, he has to understand the pattern. And that's where Watson comes into picture. So if you tell Watson that, this is WannaCrypt ransomware, these are the indicators, it tries to connect the dots, and given a behavior, it would, within a minute or so, come up with a pattern and say, yeah, by the way, I've seen this pattern which is connected to these malicious indicators, and these malicious indicators are related to a WannaCry ransomware. And then the security analyst can take a responsive action, right? So either patch it, remove it, things like that. I'm going to show you a demo to make it more intuitive, but I hope you get the point, right? So what Watson is, and where we applied the same analogy with medicine to cybersecurity as well. So it's basically from a cognitive perspective, right? We're trying to outlearn the security threats that we see day to day, with a more cognitive pattern which learns, reasons, and responds to it. Okay, and I stress upon the reasoning part, because it's very easy to basically have a database of structured data which contains trillions and trillions of data, right? So many URLs are malicious, so many hashes are malicious, so many domains are malicious. That kind of thing is good, but being able to reason behind it is what's cognitive all about. So you probably heard about firewalls, IPS, antivirus scanners. You probably have one installed on your laptops, right? So these are all silos. These are all perimeter controls, which basically saying, okay, I won't let these things in, right? That's all perimeter controls. And then what happened is people wanted to go into a more mature model, where they talked about security intelligence, right? It's able to correlate stuff from different sources and able to raise an offense which basically goes through a lot of events, right? Because what happened is, eventually, as the industry matured, you had a lot of these security events happen. These are not one or two or three events. These are tons of events happening every day. So it'll overwhelm anybody who is looking or manning the security operations center, especially at an enterprise level. If you look at any bank or any financial institutions, you're probably seeing close to good 10,000 to 20,000 events an hour, actually. And for somebody to analyze each of those events is just not impossible, and doesn't make sense at all. Some of them could just be somebody trying to do a recce on your system, and somebody trying to scratch on or knock on firewall does not mean anything, right? Because it hasn't gotten through the firewall. So to prioritize some of them and being able to use the time properly, right? That's when the security intelligence came into picture. So you have this central piece where your network endpoints, your firewalls, your IPS, your fraud detection systems, your identity and access systems, all of them are sending their events to. And then it's correlating the logs being sent by the applications as well, right? That's what security intelligence was. Your SIEMs are essentially security intelligence equipment out there helping the centralized manned security operations center. Right, that's what is SIEM. Have you heard about QRadar before? QRadar, Splunk. Okay, so those are the SIEM type of controls that people use in a security operations center. Okay, that was somewhere around late 2000s, and it was still popular a couple of years ago, right? And a lot of this intelligence that we're being built, right, that they're essentially on top of these SIEM technologies. So 2 years ago, as I told you, we started doing cognitive security, which is basically interpret, learn, process security intelligence that was designed by and for humans at a speed scale that like never before, right? So all of this, when somebody mans a security operations center looking at QRadar or an SIEM, these offenses for investigation takes a lot of time, and you don't have that many people looking at it, right? Even if you take the number of offenses that show up at a financial institution, there are a lot of them. So we had a skill gap, number one, because the analysts were we never had a really good analyst, who was top of his game, right? It was very hard to get. There was a skill gap. Not everybody were pursuing cybersecurity as a career option, right? People wanted to become developers, engineers, big data, as whatever you told, right? Machine learning specialist, IoT specialist, but never. I don't hear, from a lot of engineers that they would want to become a cybersecurity analyst manning a SOC, right? And I don't know how many of you want to. So I don't want to push you in that direction of career, but I would like to say that, as hacking is more interesting, defending from hacking is equally interesting, right? So we don't see passion in some of these security analysts. I mean, we have about 7,000 people sitting in our second floor EGL block who are actually manning the security operations center for customers, right? So they're looking at Equifax offenses, and you know what happened with Equifax a couple of years ago, or 6 months ago, or something like that. So, they're looking at constant events coming up or offenses showing up on Curator for these customers and trying to evaluate what's going on. Some of these are real offenses. Some of these are probably trivial or probably defended by an existing infrastructural element. So there you go. So we came up with this cognitive security element, which is part of the SIEM, which is able to learn, reason, and react to a particular offense and learn from it. As I proceed through these slides, right, some of this is meant for marketing material. So, I'll probably talk more about stuff like what would it take to build a cognitive system versus what we're trying to sell. Okay. So when we began this project, we had to teach Watson the language of cybersecurity, right? When we began on a clean slate, we asked Watson what the ransomware is. It would come back and say, yeah, it's a city with a population of 200,000 people. To its benefit, right? So there are 7 cities in the U.S. which are called ransom, and it probably confused with that. And then we started ingesting data. As part of ingestion, right? What we do is we actually take a document. We have something called Watson Knowledge Studio. We load the document into Watson Knowledge Studio. These are all the tools that basically help in identifying the relationships before ingesting into the system called Watson. We load this document into Watson Knowledge Studio, annotate stuff, right? Annotation is basically take the entities. You have WannaCry, which we identified as ransomware, and we define what ransomware is, which is a malware family, right? And then we kind of tell what a ransomware would involve. It would encrypt a disk, and it would hold you at ransom. That's what ransomware does. And one of the course of action or action objectives would for a ransomware would essentially be somebody browsing through an onion browser and paying the guy who held you at ransom with bitcoins. And that's if you notice all that behavior, it's very typical with a ransomware pattern. Okay, so going back to annotation, so we take these verbs, the things like malware, hashes, URLs, domains. We annotate them as part of the document, and you don't have to annotate it for each and every document. It's the initial process was the toughest part, because you need to tell Watson what cybersecurity's terms and language really was, right? And just like you learning what cybersecurity terms are, we're teaching a machine to do the same thing. You probably have never heard about. Let me tell you this: course of action, or exfiltration, right? Or what do you call reconnaissance in cybersecurity aspects of it, right? So there are certain terms that are associated with cybersecurity, that a machine would not probably know unless you teach it. So that was the annotation product. So we took all these blogs, Wikipedias, structured data that we already were curating from our research, right? All those materials were essentially text at some point. We started annotating that and ingested into this corpus called Watson. So after probably ingesting about 1 million documents, it was at a fair state. Now you ask what ransomware is, it would come back with an answer that would be more in line with what a cybersecurity analyst would like to hear, right? So And then we had this problem of, we ingested all these million documents. We are continuously ingesting the latest blogs, latest feeds that we're getting from security research and all that. And then we had this problem of, too much of data. If you ask something, it was throwing a lot of connections with us, right? So when we ask about a hash, that hash probably reincarnated into multiple malwares, right? People usually copy and build malware on top of it. They don't essentially start on a clean slate, right? Because people share data. So if a malware could, essentially beat our defenses, enter the enterprise and start spreading, they would use the same methodology for building a newer ransomware. Probably tweak it a little bit so your existing frameworks cannot catch it. One such defenses is the DGA thing. So we have these WebSyn software, we have these firewalls, we have these IPS devices sitting in the infrastructure where we're putting rules saying, okay, don't allow these domain names, don't allow these categories of URLs which are known to be malicious, right? We all do that. That's how. So what the ransomware guys do is, in order to have these command and control, again a newer term, command and control is basically establishing a foothold inside the enterprise and communicating with something that's outside the network and being able to control within, perform certain things inside the network, right? That's what command and control is. In order to do command and control, you need to bypass these protections or get past the firewalls and IPS. So they use a methodology called DGA, a domain name generation algorithm. So it comes up with abcdef12345.com, and you have this domain translated to certain IP address, but that domain isn't classified to be malicious because nobody knows about it. It's a very randomly generated domain name. Right? If you go to X-Force Exchange and query this domain name, you probably won't find any entry in it, just because it's dynamically generated, and you have these fast flux domains, right, which are changing the IP addresses pretty fast, right? So that was one of the symptoms of typical ransomware, and we all have to teach Watson about it. And as I told you, this. When you asked Watson certain things, it was throwing too much information, and our customers always hated having too much thrown at them, right? You tell me what's happening, don't tell me that this could be happening, and give me a million possibilities, because you're making their lives much more tougher by throwing data at them. So what we had to do was, apart from just using this cognitive corpus and asking Watson, we had to somehow marry the data with our structured corpus. Our structured corpus would actually mean a specified structure, pattern for security. For example, if you give X-Force Exchange is one of these research databases that we have, and if you give it a URL, a domain name, it would classify that into a certain category, and it's slam dunk for most of the analysts, because if it tells that this is malware, it is malware, right? They don't have to go research and figure out if a particular file with a certain hash is a malware, right? Otherwise, they would end up doing sandboxing, figuring out from endpoint software whether this has modified registries, this has played around with certain file systems and all that, right? It takes a lot more time. So what we did was we took that security data that we were already building and married with what Watson was saying, and came up with this cognitive software that would actually help the security analyst sitting before a SIEM to zero in on an incident. All right, something for you to, trying to make this more impressive, right? So what did we achieve after we used Watson, right? We gained powerful insights, because certain connections are not, imagine an attachment that you get, right? Do you still get .exe attachments? You probably don't, right? People have gotten smarter and they don't send you .exes anymore. They're sending you a PDF file, or probably a Word document from a legitimate source, like your professor sending you an email saying, here are your grades or whatever. And there are macros inside that Excel document or Word document that would install a JavaScript. It doesn't have to do an installation of a real malware binary. If you look at how WannaCry or Locky spreads, it installs a JavaScript. It's a .js file. That's all it is, and you have to run it in a browser. And all what it does is it would basically connect to a URL and download the exe for you. wget, simple, right? So when you look at .js file in an attachment, or if a macro executes that, you probably won't notice it. And your email servers, which are probably running malware scans, cannot detect it either. So to be able to see this connection that you got an email from some recipient or from some source, and this has an attachment that executes a macro that downloads a JS file, that downloads the real exe, and that exe copies itself into a registry. So when you restart your laptop, it's restarting, it gets installed or whatever, right? And it renames itself and copies itself into your temp folder. And it also would change certain properties of that binary, so people would not know that it has been downloaded from internet, right? It's a matter of just editing a property on a binary. It all happens, right? And to be able to connect the dots, it takes a real researcher to do that. It's not possible for a let alone a expert, right? So I'm even talking about the guys who are sitting before SIEM. They don't have a clue about what's happening, because it's happening at an endpoint level. So to connect those dots and explore the possibilities, it was humanly impossible, and that was one of the problems that cognitive security was trying to solve. So it gave those connections, all those powerful insights that we would not be able to connect, because when we ingested those relationships into Watson, what it did was it connected. Suppose a hash was connected to another hash, right? Your file may not be opening, may not be malicious, but it may be opening another file which could be malicious. So all those connections are established within Watson, and it was able to come up with that. Obviously, this happens within a minute or so, and versus 6 months, 3 to 6 months that an analyst would take to establish, certain malware happening. This was a famous case with Sony. They had the best of the cybersecurity analysts sitting before SOC. It took 6 months for them to figure out that something was happening, right? I mean, not because they had dearth of talent, but because, it's humanly impossible to make those connections. And if they were using Watson to apply obviously their SIEM was throwing up offenses saying, oh, this is happening, this is anomalous. And that's about it. If you look at any of these SOC entities, all they'll tell you that this is anomalous, this is out of the norm, things like that, right? But it doesn't tell you what's really happening, right? And anomalous could be as simple as somebody emailing with sending an email outside the network with code attached to it. It could be, it probably need not be a dual code that somebody's trying to exfiltrate. It could be, a simple in a for loop that somebody wanted to keep it in their email account or whatever, right? Things like that. So there's a lot of noise, no doubt about it, when you look at a SIEM level. But to be able to narrow down to something that was more important, that was more connected to a malicious software, was a lot more important, right? So in order to save time and cost, they had to use this cognitive security element as part of the SIEM. They talk about ingestion. We talked about annotation. So you hear these words in the cognitive world anyway. So it's good for you to understand, what annotations are, what ingestion really means, what learning is, what reasoning is, and what experience that you would get from building a system called Watson, system that would resemble like Watson. Have you seen any videos before on Watson? You did? Some of them at least? Some of you guys? No? Okay. All right, you should try Googling it. Do you have, if you're connected to the internet, just Google, Watson for health or something like that, and you would see a good video. Some of that is exaggerated for sure, because it's not the same Watson that played Jeopardy that we are using to build cybersecurity, right? It's an umbrella where we are calling any cognitive solution as Watson. Okay, but it'll give you an idea where things are, because what happens in IBM is we set a target saying, 2 years down the line, 3 years down the line, we have this intelligent machine. You ask a question, it'll answer it'll answer it appropriately, right? And it's nice. So we have this SIEM, you press this Ask Watson button, it'll tell you, okay, it'll give you the answer that you want, right? Key in an IP address and ask Watson about it. It'll probably throw up all the relationships, the whois data and all that kind of thing. So in order to build a system like that, we had to ingest threat databases, research reports, security textbooks, vulnerability disclosures, popular websites, blogs, and social activity. These have to be continuously ingested because security is all about staying on top of the game, right? Because all these things keep changing. A hash that was detected 5 years ago is no longer relevant. You need to be able to track the latest hashes, latest URLs, latest domain names that are malicious. So you're continuously ingesting this thing because we have annotated it already. It's able to process this data at a good pace and able to connect the dots or connect the relationships automatically inside that system. And what about learning? So we have these rich dictionaries that we already ingested as part of annotation into Watson to link all relationships. So if you look at a threat name, right? So call it Zeus or call it WannaCry. If you say this is the hash connected to WannaCry, and these are indicators of compromises, and you have this binary associated with it, it's able to link those elements together. And then we basically so this is an interesting slide, right? So we took Lockheed ransomware. It's something like WannaCry, which had multiple reincarnations, and what it would do is it encrypts the files, and you have to pay the ransom in order to get the decryption key. And Zeus would steal your bank credentials. You basically are giving it a behavior, a related verb, and you're actually introducing a rule that would detect that. So that's how Watson picks up, right? So what you take the annotation logic, you apply annotators to a text, and then you get this huge graph called knowledge graph. And knowledge graph is a very common term that we use these days. It's basically a graph database. Have you read graph theory? I think you're in third year, right? You must have gone through it, right? Nodes, edges. Okay. Have you worked with any graph databases? Neo4j? Very good. At least you understand what that is. Okay. So Titan, heard about it? Titan, yeah. So those are all graph databases. Graph databases are basically, redoing your 12th grade again, right? Because you learned about permutation combination graphs in 12th grade, I guess, right? If you have three, okay, let's start with a question to make this interesting. So if you have a pentagon, how many diagonals are possible with a pentagon? Diagonals are possible with a pentagon. You all wrote some entrance exam, right? No? What do you write? NEET? No, you don't. It's not NEET. What is it called? CET. Do you write CET to get in here? Yeah. So how many diagonals are possible in a square? 2. Very good. With a pentagon. How about an octagon? Definitely more, right? So yeah. Obviously, you haven't read the permutations and combinations. So basically, any side that's not okay, any line that's connecting the edges, connecting the nodes. So how many corners do you have in a square? 4, right? So how many lines can you draw between 4 points? 2 points. 2 points, you can only draw 1 line. So in order to draw a line, you need 2 points. So in order to draw a line between 4 points, 4 different points, you get 6 lines, right? So, and there are 4 sides. So if you remove number of lines minus 4, you'll get the number of diagonals. So same thing, you extrapolate that to however many points you have. With pentagon, you have 5 points. So 5 combination of 5 with a combination of 2 points. If I see 2, right? Minus 5 is the answer for anything, right? So graph theory is essentially the same thing. So you have nodes and you have edges connecting them, right? So if you use a graph database, what do you do to query a graph database? What is it called? The term is called traversal, right? You start at certain point, traverse through nodes, and figure out the connections, right? So it's interesting where we are taking this fundamental thing like graphs and trying to solve the problem of cybersecurity, because you have these nodes which have certain properties. The node could be a hash, the node could be a URL, the node could be a domain name, node could be a malware itself. And in order to get from one point to the other, right, in order to establish a hash connects to a malware, you may have to go through multiple hops. That's called traversal. If you do an intelligent traversal and are able to get to a malware, obviously this hash connects to the malware. If there's no path, then it's not connected, right? So you've heard about paths, traversals, okay? So it's all being applied here in order to solve a real world problem. Okay, so pay attention to your teacher who's teaching you graph databases. All right, so now we taught Watson what the latest vulnerabilities meant, what the latest malware does, and annotated and ingested millions of documents into it. So now if you ask a question, what vulnerabilities are relevant to a CryptoLocker infection, it would basically search the corpus that we have ingested and extract evidence, score and weigh, and actually give you those relationships. When you look at it, it may be like 3 different vulnerabilities that are associated with CryptoLocker, but if you click on each of them, it would connect to the real evidence, meaning where did it get that information from? It was probably from one blog, or probably from the structured database that was ingested into Watson, things like that. So this machine has already learned the technique of analyzing stuff to dig the information that we need for fetching the vulnerabilities related to CryptoLocker. All right, so again, this is all why cognitive security, right? So if you have the human-generated knowledge is growing. It's something that you can impart, and you have to probably teach a machine to do that. The cognition part, right? Reasoning and learning. If you learn that something has happened, if you learn that a malware copies into a temp directory and does certain things, next time around, if you're infected with virus, what do? You look for certain things. I mean, I do this, right? So I don't. If I forget to renew my antivirus scanner, or antivirus license, what do? I try to remove malware myself. And what do I do to do that? I go search for certain EXEs that got installed, right? And we all do that. We'll do that, right? And then delete it. What's getting started? Go edit the startup and then delete modify the startup things. Because this is what a typical malware does. It modifies your startup process. It modifies your registry, things like that. So you go edit, clean it up yourself if you have not renewed your antivirus license. So that human-generated knowledge is something that we are trying to help teach Watson, to connect the dots, to see certain behaviors and traits that are very typical with a malware. And it's growing, right? So this data is growing by the day. I know because I ingested this XFE or X-Force Exchange research data into graph database. This was close to, just alone for hashes, we are ingesting close to about 200,000 documents every hour. Okay, and you can't imagine somebody being on top of it, right? So it's a lot of data that is growing, and some of that falls off the radar because people are no longer using that technique. So we have. Again, this is a good point there, right? So a typical organization can only leverage up to 8% of this content. So it really is talking about, there's so much of data out there, big data, right? This is not about big data. It's so much data out there, and being able to learn all that, reason, and then act upon it is humanly impossible, and hence Watson is there for you. Okay, this is something that we try and explain people, like why cognitive security, right? I look at an offense, I do certain searches on Google, I do some search on known databases, virus total, and things like that, and I'm able to get that information. So why do I need Watson? And we ask the same question, how long do you take to do an analysis of a particular offense that occurred at a SOC level? Usually, right, they say an hour, 2 hours, 15 minutes, things like that. But the real malwares that infect, or zero-day threats that happen, right, it takes a lot of time for them. Most of the cases, they probably won't even come up with an answer for the offense. They won't close the offense for 6 months because they have no clue what's going on. And it's a constant race, and they're also overwhelmed because you probably employ like 4 or 5 guys to look at your SOC, because you always think that nobody's going to attack me. We have these firewalls, we have these IPSs, so it's not going to happen. So you don't invest your resources in just looking at offenses that are happening, unless you're a banking system, right? Because if it hits a banking system, you're losing money. But if it hits a university like you, it probably does not cause a lot of impact. So all the more reason, you use a corpus like Watson to minimize the costs and minimize the time that takes for anybody to look at an offense. So what I'll try and do is I'll try to give you a perspective of what happens in a security operations center, right? So this is our QRadar product, and it's all like make-believe thing, okay? So I can't show you a live demo because I have to be connected to an IBM network. So I'll play a recorded demo which would talk about where this cognitive security came in from, what it tries to solve. This is a typical medium enterprise where, certain things are being thrown at the SOC analyst. There's suspicious action from a document, certain vulnerabilities, potential data leak, all these kinds of things, right? All it's telling you is it's potential, it's anomalous, things like that. It's suspicious, that's it, right? It's not telling you that, oh, by the way, that suspicious action really relates to installing a malware which would connect to this command and control server and would encrypt your system. It's not telling you that. It'll be really useful for somebody that your attack has happened and it has gone through certain, because it usually does not happen in one shot. It goes through something. For example, take a Mandiant life cycle, right? It installs, it establishes foothold, establishes communication with command and control server, then performs the action, right? Because if it happens so fast, your what do they call it? The sandboxing equipment will catch it, right? So it's a defense against sandbox equipment. So the slow process of establishing foothold, doing a lateral movement, or how it spreads, how does it encrypt, takes the action, that kind of thing is not detectable. But to tell an analyst that I have seen an action where it was talking to a command and control server, but haven't seen exfiltration would mean a lot, because that really means the attack hasn't succeeded, right? So if you look at any SIEM consoles, it's basically telling you that my rules have fired, and it's a suspicious action, and that's it. That's about it. It's suspicious. But it's not going as far as connecting the dots and actually telling what's happening. And that's the real job of a SOC analyst, to go behind it, figure out the connections, and raise a incident response ticket if they need to take an action on it, right?
Enterprise type scenario, scenario state. Or
so what we did was we basically detected a potential
But a lot of times, as we said earlier with Raphael, you end up something with
that's
their
the
document.
And
what
then,
event is there?
Let's see what Watson said about it. So, it took few of the observables from the suspicious action document, be it hashes, be it the communications that were noticed. And what happened was we gave it for analysis with Watson, and Watson came back and determined Locky malware family or that could be associated with this incident, right? There are 5 other assets in the network that appear to be infected. And it also found these additional indicators, that could be related to this thing. So it basically zeroed in on a Locky malware campaign. So that's the text part of it, right? That's human telling you that, oh, I looked at the incident. By the way, it looks like Locky malware. Let's go, patch it or do something about it, right? That's exactly like a human talking or giving a response to you. It's just text, but you could imagine a voice behind it. So we did that.
And QRadar is going to get a whole bunch of information
for any
about
secure
it.
analyst,
Just
throwing something at them,
of, what is the host, what networks is it putting it on, and is it sitting on the partner network, maybe a business owner, what kind of operating system is this?
Right.
All of that information gets pulled into here.
And then
but we're also seeing here that,
what the proof is.
It is there.
And this is your graph
family.
database, right?
We
So
can see there's a bunch of documents
at,
it believes to be related to this.
So many attack campaigns
and as
were
well,
found. It's still,
there's a bunch of
the same
different assets
information
in
that
my
was in the
network
text,
that are involved
right?
in this.
It didn't tell you how it
part of this original suspicion.
How it evolved to that conclusion. It found that somebody downloaded an exe from .com, and then there are so many other assets that got impacted because they also were doing the same thing. I'll get to a bit, where you could make those connections, and this is a graph database, and try to get this right, okay? Because you need to be able to appreciate what you're learning in your graph theory. So it told all these things. So let's go back and
Lockheed is on this single suspicious incident from. This is really good. We want to go explore insights.
Okay, so I hope you can see those small things. But if you can't, the dot in the middle is the Lockheed malware campaign. So what you see is that in the bottom, you have a 10.IP address, right, which is your local laptop address, which is communicated to certain IP addresses which were in, I believe that's the Russian flags, the Russian Federation. And then they have downloaded a year-end.xls, which is the Excel spreadsheet, which installed an exe. And after that, you saw a communication go to scarpina.com. And it downloaded an exe, which is related to Lockheed. And, you see the other 10.IP addresses, communicating with certain domains, right, which are also connected to Lockheed, right? And you actually see the tar project there, right? You know what a tar project is? So tar project is where you download the onion browser from there, is right. So onion browser is like an onion, right? You peel one at a time, and you won't be able to understand what the communication is, right? So if you use a regular browser and connect to anything, people can read it, right? Even if it's encrypted, you could do a man in the middle and read it. Onion browsers are created to not to make it impossible to decrypt to make it impossible to know what's happening, what websites are being hit. So Bitcoins is all about secrecy, right? It's all it follows blockchain, but it's built on blockchain, but it's more cryptocurrency. Nobody knows what's happening, who owns it, who's transacting, no such thing, right? Exactly. It's all anonymous transactions. So onion browsers help. If you download onion browser and pay in Bitcoins, nobody would know that you have done that. But the only thing that we were able to detect is somebody actually contacted the tar project, which is not a good thing, which really means they have downloaded onion browser from it and then they paid in Bitcoins. Okay, so go Google it, try to understand how this onion browser works, what a tar project is, so you could become future hackers. So what you see is communication, that 10.IP addresses, communicating with the tar project. And in the next screen or so, you would actually see that one of the 10.IP address belongs to an intern, which is not always a good thing, that he's paying in Bitcoins, right? So that gives you a picture, right? That gives you a context. It's just not that Watson determined the Lockheed malware association. It also showed certain behavior which were likely to be associated with a Lockheed or ransomware behavior, right? That's what that is. And
final state of Watson, what the advisor and Watson are at the center of this. That's basic security to this particular.
So here is the proof. So how did it determine that, right? So it basically said, I looked at so many documents and so many domains were found, and then I determined so many relationships, right?
Work with a number of different
Let's look at it.
And
then when you click
and we can see here that there's a number of different documents
you would actually see the documents that we
to
fed to Watson. These were all the blogs, or probably if you look at the McAfee blog or the PDF file that was talking about the threat advisory related to the ransomware Lockheed, it was all ingested into Watson, and it's able to use that to determine that there's an association with Lockheed malware.
Decision. We can add to the first stage of this, where Watson and the advisor started with that single piece of information. And first, if I could actually say that, I've had this suspicious event, if I could actually say that.
So this is what I was talking about. So what it does is it also pulls in
suspicious event,
local context, which basically says, this laptop belongs to one of the partners who's currently working on, he's the intern that were hired to do certain things. And it's not always a good thing that, somebody like an intern went to a tar project or downloaded a malware or exe, which is not always a good thing, right? So it gives you the local context.
This particular Excel document that somehow placed and executed just a bit, looking at all the different categorizing, but was pulled out data mining all of this himself. But that was done automating this.
And then what you would see is that in some cases what happens, it also as I told you, these hashes, these malware behavior are usually copied and replicated for other malware. So it also found an association with Dridex malware. And in a bit, you'll know that, why we dropped the Dridex node from the graph, because it sort of is irrelevant in this particular investigation. And so you found the relationship with Dridex and malware because you were able to see the tar project communication. We kind of decided that the Dridex malware was not relevant, so we dropped that node from the final graph that we present to the analyst. So it's basically a product of how we use Watson, right? How we use Watson to zero in on an incident. We mine the indicators locally, analyze, give it to Watson to analyze it, bring that back, apply the local context, and then look at the connections. And in this particular case, we took a suspicious activity, which was basically saying some exploit was, some suspicious exploit was noticed, right? We took that simple thing, we mined the indicators, and we were able to connect the behavior to a Locky malware campaign. And we also saw the other communications to the tar project, which kind of proved that it's most likely a ransomware. Right, and in this case, somebody can go ahead and open a Resilient ticket, which is our integration into the product, right? So basically say, we basically can export this into a Stix. Stix is a standard where we document an attack. It has observables, indicators, everything captured in one document that any security guy would understand universally. And we take that and send it to Resilient, that is. Okay, so that's the whole process. You start from an offense, ask Watson, bring that back, apply local context, drop the things that are not relevant, and then zero in on the incident, open a Resilient ticket, and close the offense. That's the life of a security analyst sitting on sitting in a SOC, trying to do his job. I hope this was useful. A lot of this may have gone over your head just because it's industry, but what I would like you to take back is the technologies that we use. We talk about cognition, we talked about graph databases, and how important is it to understand graph databases. If I show you a query that we do on a graph database, you would appreciate it, because the traversal is so complex that we start from a domain name, we see what it resolves to, an IP address, and we start from that IP address, go see if there are any connections to hashes, and see if those hashes are related to malware. And it's a traversal that's pretty complicated, and that's that's something that you need to understand, that we can use graph databases for doing these sorts of things, right? That's what I was telling you. The DGA and other stuff, the malwares are smart these days. They know how to bypass the defenses. It's signature based stuff usually applies at a firewall or probably antivirus or IPS level, where you're looking at certain network pattern and saying, okay, this is signature belongs to malware, so let's block it, that kind of thing. This is after the fact. So this really, any SIEM is after the fact. It has crossed the first lines of defenses. It has affected your network, and SIEM is capturing that behavior as anomalous or suspicious, and you're doing investigation on top of it. So Watson is not actually doing anything to relate with signatures, but if a certain virus signature captured it, right? There are like good 100 or odd scanners out there. So if some scanners reported that a particular hash was associated with certain malware, it's usually the case, right? Some of them are latest, some of them are behind the curve. So Watson, because we are ingesting all that data into Watson, we know that if 10 different virus scanners reported a hash to be associated with a malware, then we are able to catch that, right? Okay, so we're teaching Watson what other people, what's out there in the world already, right? And it's not signature-based matching as much as more applying learning techniques. We're teaching Watson that, this virus scanner found out that this hash was associated with this malware. So if you see this hash in the investigation, and you do your traversals or connections, and then figure out and use that the connection to establish the malicious association. Right? It's nothing to do with the virus signatures per se. Train neural network and managed graph. So I'll tell you what I know. And this is every time somebody talks machine learning, I tend to froth at my mouth. But for what it's worth, so there are a bunch of algorithms where you're giving certain. There's this concept of training the neural network itself, right? So let me give you an example. Maybe it's better. So you have certain classifications in the structured data, right? So certain observables belong to a certain part of cyberkill chain, for example. So if you have certain behavior is associated with exfiltration or command and control, right? So you would have those things in place, and that would have certain properties associated with it. So we teach the neural network saying, these kind of IP addresses with these kind of properties are usually associated with command and control, right? Now you give a random IP address to it, and it looks at the properties of it, and since it learned stuff from what we ingested already, it's able to say that, yeah, this could be command and control. That's machine learning to me. But there's no reasoning behind that. It's more like algorithm mesh type than how a human would act. This is more about how a human would act. So you would usually learn, as a child, you would learn a language, right? As you grow up, when I talked about the graph theory and all that, you picked up that thing and you won't forget it because you learned it. Machine learning is more based on the models, the patterns that it observes, apply an algorithm on top of it, and see if you can, find the output based off of that. And the input and output are sort of predetermined. Versus in a cognitive sense, it's not predetermined. No, knowledge graph is capturing the stuff. It's like how your brain is connecting to it, right? So if I say selection, right? So how would you connect to me? So you would connect to that lady out there, and then say, yeah, this girl invited me to this ACM conference, and I'm from IBM. So there's some connection to IBM through you, right? Something like that. So all these connections are put in a graph, and you're able to reason behind why I'm here, right? So cognition is really about applying those techniques which would learn, reason, and act upon it, right? Machine learning is a totally different thing. Machine learning is this, I would call it a hunch, because you're throwing certain data out there, applying an algorithm on that pattern, and trying to get an output. Right? You adjust the weights on the network, and you somehow get this output. You do this 10 times, the 11th time you could be right is the perception there, right? And that's why machine learning is pretty expensive. It's not, if you give it like data that's 100% malicious, every time you throw something at it, it'll say it's malicious. But if you give it a mix of data, right, and then ask a question, it'll probably be able to find the right pattern behind it. But it's still finding pattern based on what it's taught, right? What it's been given, the data set that was used. There are different techniques, but I probably talked about one of the techniques in machine learning there. But cognition, this is different. Don't confuse with cognition and machine learning, right? So you can apply machine learning on top of cognition, but this is not essentially machine learning. Okay, good question. This is the question that one of the customers asked, right? When we go sell these products, right, there are competitive products out there which just says, oh, I use machine learning to determine this. So what do? I said, well, two different things. Don't mix these things, right? We're trying to help a human. Like nobody can replace a human brain, obviously. And the only challenge is that the human brain cannot. It's impossible to stay on top of things. And that's why you're using a machine to substitute a human brain, right? It can never reason, and a machine can never replace a human brain. So Watson is all about getting there, making a machine as intelligent as a human. It's just, we will get there, because this challenge was thrown at us 2 years ago. We're still not there. We still are not there at a point where we could basically say, be as accurate as a human can, but looking at the same set of data. Right? It's still a lot of information is being thrown at analysts. It reduced his time, but it did not replace him. Just like we can't replace doctors, right? A lot of people do Google before whenever they get symptoms. I have headache. By the way, I have also this. Let me Google and take some medication. Right? It's a very dangerous thing. You can replace a doctor. You just can, and just like that. You can use an assistant to tell a doctor that I looked at these studies which were relevant to this. So it helps the doctor look at the same studies and make a decision. But you can't make a decision. The machine cannot make a decision for the patient there. You got to remember that.
Is this an open source project?
There is certain parts which are open source, and if you're interested to look at it, I could get you connected there. But Watson itself is some sort of a trademark system from IBM. There's certain portions of it which you could use to build a cognitive system. I wouldn't even go there. I would actually go onto IBM Cloud. So IBM Cloud has this Watson APIs. So one of the interesting things is sentiment analysis, right? So when I get a manager from an email with some sort of directions and stuff, I stick it in Watson and it'll tell you this guy has a negative mood, by the way, right? So that kind of thing. So it's fun. I'm sure you write emails, right? Or mostly WhatsApp, or take a WhatsApp message, stick it in Watson, see what the tone of the speaker was, the guy who wrote. So it's interesting insights into it gives you the tone. It gives you certain other characteristics of that particular text. So there's text analysis, and that's an easier one. But there are a lot more complicated stuff related to accounting and extrapolations and all that. So ingest some data, use those APIs. I would start there. Go to IBM Cloud, go to Watson APIs, and see if you can use 2 or 3 of them to build your smart application, right? Right. Like for example, maybe this is a challenge for you, right? So you write essays for your answers, right? Something like that. So see if Watson can analyze and say if it's correct or not, right? See what would Watson score you versus what your teacher scores you, things like that. You could build a cognitive application, essentially remove evaluation as from your, as a job of teacher, right? They do look at your papers. Maybe Watson can look at it one day.
And is this going to be an internal project for IBM, or is this going to be
This is
rolled out
public.
to- This is public.
Yeah. So the difference between, Shriek spoke at length about IBM Cloud, and I don't want to steal words from his mouth, but IBM Cloud is a platform. It's called Cloud and Cognitive Platform. So if you look at AWS or Amazon and Google Cloud, they don't talk about any of these things. A lot of people talk about big data, machine learning, all that crap. But the differentiator between IBM Cloud and the other clouds are we are a cognitive platform. If you build an application, build a cognitive layer below it. Yeah, you'll have infrastructure, you'll have algorithms, you'll have application logic, but you have to build it on top of a cognitive layer, and that's when you're ahead of the game. Right. So IBM Cloud is the platform where you can build a cognitive application. So I would start there because you don't want to reinvent the cycle. Right. Get the fundamentals right. Understand what cognition is, right, through your coursework or whatever, and then apply that in using the cloud, leverage the cloud, and build an application that you could think of for your probably an undergrad project or something like that. Right. I'm sure your faculty should get in touch with the industry and talk about changing the curriculum to include more cognitive stuff, because we're betting on it big time, right? Because that's the differentiator. I hope this was useful. Thank you.